Imagine a cosmic speed limit. Like, not for cars or the speed of light, but a strict mathematical speed limit for numbers themselves.
Oh, yeah.
If even a single number in the entire universe breaks this speed limit after the number 5040, then the biggest unsolved problem in mathematics just completely collapses.
Which is wild to think about.
Right. We're talking about the Riemann hypothesis. And usually, this topic comes with the expectation of just impenetrable complexity.
Oh, absolutely.
Just like a bunch of zeta functions and imaginary numbers and the complex plane. It is notoriously intimidating.
Yeah, it's really the ultimate kind of do not touch mathematical beast, right?
Yeah.
For anyone without an advanced degree in analytical number theory anyway, I mean, the traditional approach requires you to understand how primes are distributed by looking at zeros on a complex plane.
Which makes no sense to a normal person.
No, exactly. It's completely divorced from how we interact with numbers on a daily basis.
And that is exactly our mission in this deep dive. Because we have this fascinating stack of sources in front of us today, including these mathematical papers and notes dated August 25, 2026. And the standout piece is this brilliant paper titled Exponents Don't Matter.
Such a good title.
It really is. And what these sources do is they strip away all that academic jargon and they translate this million-dollar complex math problem into a structural secret about just basic arithmetic.
Yeah, basic division, really.
Right. It turns out proving the Riemann hypothesis is mathematically identical to proving a simple rule about how numbers divide.
And to bridge that gap, we have to look at the fundamental relationship between prime numbers and divisors because, the Riemann hypothesis is ultimately a question about the chaotic distribution of prime numbers.
Right.
But prime numbers aren't just abstract concepts. They're the atomic building blocks of every other number. So when you combine primes, you create divisors. So knowing the absolute maximum limit of how many divisors a number can have inherently requires perfect knowledge of how those underlying primes are distributed.
Which brings us to the core concept we need to unpack today, which is this idea of abundance.
Yes, abundance.
To understand this cosmic speed limit, we first need to understand how we measure the weight of a number's divisors, right? So let's take a common everyday number like 12.
Sure.
If we want to find its abundance, we start by listing every whole number that divides into it evenly.
Yeah.
So for 12, those divisors are 1, 2, 3, 4, 6, and 12 itself.
Right, and then you just add them up.
Yeah.
So the sum of those divisors is 28. And to find the final abundance, you just divide that sum by your original number. So 28 divided by 12 gives you an abundance of roughly 2.33.
2.33. Okay, and if we compare that to a slightly larger number, say 13, the difference is just staggering.
Oh, yeah.
Because 13 is a prime number, right?
Yeah.
So its only divisors are 1 and 13. Add those up, you get 14. Divide 14 by 13, and its abundance is barely over 1.
Right.
So size alone doesn't guarantee a high abundance. It's entirely about the internal structure of the number.
Exactly. And mathematicians naturally began to wonder, well, just how high could that abundance go as numbers stretch toward infinity? Like, is there an upper limit to how heavy a number's divisors can become relative to its size?
Yeah.
And the sources we're looking at today boil this massive question down into one incredibly intuitive foundational formula.
I really love how beautifully simple the sources make this. Because if we boil down all of this complex number theory into a single formula that anyone can understand, it's just this.
Let's hear it.
A number's abundance is approximately equal to which primes you use multiplied by a tiny exponent adjustment.
Right, which primes you use times a tiny exponent adjustment. The structure of a number's total abundance is basically fractured into those two distinct mathematical parts.
Okay.
And the first part, the prime support, that is the true engine of abundance.
The prime support.
Yeah. The most efficient way to make a number's abundance skyrocket is to construct it using many small, distinct prime numbers.
So we're talking about 2, 3, 5, 7, 11, that kind of thing.
Exactly. Every new prime divisor you bolt onto your number acts as a really powerful multiplier for the divisors.
Yeah.
But the smaller the prime, the more massive the multiplier.
Oh, that makes sense.
Yeah, having a dimper 2 as a base divisor provides a far larger structural boost to your total abundance than having a larger prime like 17.
So if your goal is to build a number with maximum abundance, your first strategy has to be hoarding just an uninterrupted sequence of the smallest possible primes.
Right.
You cannot skip any.
You really can't. But the second half of that formula is where the mathematical behavior becomes deeply counterintuitive.
This is the tiny exponent adjustment part.
Yes, the tiny exponent adjustment. So the sources highlight a proof called lemma 0, which demonstrates that stacking exponents has a surprisingly negligible effect on a number's abundance.
Which is weird, right? Because our standard intuition suggests that repeating the same prime factor over and over, like taking that prime number 2 and raising it to the power of 10 or 100 or a million, that should push the abundance exponentially higher.
Right, you'd think so.
Because you're pumping more material into the number, so you expect the divisor weight to scale accordingly.
Yeah.
But it simply does not.
No, it doesn't.
I was trying to visualize this, and the best analogy I could deduce is making a recipe.
Oh, I like that.
Yeah, so when you add distinct primes, you are adding entirely new flavor profiles to a dish.
Okay.
You introduce salt, you add acidity with lemon, you add heat with chili flakes.
Right.
Each distinct element multiplies the complexity of the meal exponentially.
Right, it creates a whole new experience.
Exactly.
Yeah.
But the exponents,
Yeah.
that's just adding more of the same salt.
Oh, wow. Yeah.
You could dump an entire cup of salt into the pan, but you haven't added any new dimension to the dish.
No.
It's just aggressively salty.
Just saucy, yeah.
Doesn't radically change the fundamental structural complexity.
That recipe analogy is perfectly aligned with the mathematics in the paper. The sources prove that this exponent distortion factor is strictly trapped in a narrow mathematical window.
Like it has a limit.
A very hard limit. It bottoms out at 6 over pi squared, which is approximately 0.6079.
Okay.
And it mathematically cannot exceed the number 1.
Wait, let me make sure I'm grasping the scale of this. No matter how wildly you stack exponents, even if you use 2 to the billionth power, it can never change a number's abundance by more than a factor of 2.
Not even a factor of 2. I mean, the absolute maximum change it can exert is scaling the abundance from about 0.61 up to 1.
That is wild.
Right. Exponents are genuinely just a minor fractional adjustment to the distinct prime numbers you originally chose.
Just a tweak.
Yeah, they basically act as a fractional drag. It's a permanent discount factor that holds the overall abundance back from reaching its full potential.
So if abundance is primarily driven by hoarding small distinct primes, and exponents just act as this tiny fractional tweak, what happens when we try to push this to the absolute limit? Like, is there a ceiling?
There is a hard ceiling. It was discovered in 1913 by a mathematician named Thomas Gromwall.
Gromwall, okay.
He proved that the maximum possible abundance a number can possess operates under a strict asymptotic speed limit.
The cosmic speed limit.
Exactly. And that limit is 1.78 times the logarithm of the number.
Okay, let's translate that math for a second because it sounds scary.
Yeah.
The logarithm of the logarithm just means this speed limit grows incredibly slowly as numbers get larger.
Right, it flattens out.
It curves off. And that 1.78 number isn't just pulled out of thin air, right? It comes from Euler's constant, which is a fundamental limit in how harmonic series grow.
Yeah, exactly. So as numbers march toward infinity, their abundance is theoretically capped by that logarithmic envelope. They can approach it, but mathematically the trend suggests they should never systematically break through it.
Okay, well, I want to test this logic. Because if distinct primes are the real fuel and exponents are just a minor distraction like salt,
Yeah.
I should be able to build a number that easily hits this 1.78 ceiling.
Oh, let's see.
So what if I construct a massive number by just multiplying every prime in order? So 2 times 3 times 5 times 7, all the way up to 1,000,000.
Okay.
And I only use an exponent exactly 1 for all of them. No stacking.
Okay, so in math, these are called primorials.
Primorials.
Right.
That has to be the most efficient way to hit the speed limit, right?
Yeah.
Because I'm maximizing the prime flavor.
It is an incredibly logical strategy based on the formula, but it actually fails spectacularly.
Really?
Yeah. Primorials do not even come close to hitting the cosmic speed limit.
But why? I'm hoarding all the smallest primes just like the recipe calls for. I have all the flavors.
You do, but it fails because of that exponent distortion factor.
Oh.
When you use flat exponents, meaning every single prime is simply raised to the power of 1 more, your distortion factor crashes to the absolute bottom of that narrow window we discussed.
The 0.6079 number.
Exactly. It converges entirely to that minimum of about 0.61.
Oh, I see. So by ignoring the exponents entirely, I'm triggering the maximum possible fractional discount.
Yes. Primorials suffer a massive 40% shortfall. They fall short of the Gromwall speed limit by nearly half, strictly because their exponents are entirely flat.
Wow.
So just hoarding primes is not enough to touch the ceiling.
You need the tiny adjustment, too.
You absolutely do. To actually reach the mathematical ceiling and eliminate that 40% discount, you have to construct what mathematicians call colossally abundant numbers.
Colossally abundant numbers.
Yeah. You start by gathering those small consecutive primes, just like you did, but then you strategically stack their exponents infinitely high.
Okay.
And by piling on those exponents, you force the distortion factor to slowly climb from 0.60 up to exactly 1.
So you are basically overpowering the fractional drag.
Yes.
You stack the exponents just to erase the discount, which allows the total abundance to climb all the way up and perfectly kiss that 1.78 speed limit.
That is exactly it. That is the sole structural role exponents play in this cosmic limit. They just erase the deficit.
Okay, so we have this beautiful asymptotic ceiling that these infinitely large, colossally abundant numbers slowly climb up to touch.
Mm-hmm.
But infinity is abstract. Like, what happens down here with finite everyday numbers? Because this is the moment the Riemann hypothesis finally steps onto the stage, right?
It is. This is the historical pivot point of our sources today. So in 1984, a French mathematician named Guy Robin published a paper that established a profound unconditional equivalence.
Okay, 1984. What did he prove?
He proved that the Riemann hypothesis is true if, and only if, every single number in the universe obeys this exact abundance speed limit with absolutely no exceptions for all numbers greater than 5,040.
Wait, let's pause and appreciate the weight of that.
Yeah, it's huge.
Robin's criterion takes our intuitive formula about divisors and turns it into a strict law of physics for mathematics. Abundance must be strictly less than 1.78 times the log of the number forever, as long as the number is bigger than 5,040. But that specific cutoff, 5,040, implies something wild. It implies there are smaller numbers that actually break the cosmic speed limit.
Oh, there absolutely are. And we've actually already met one of them today.
Oh, really?
Yeah. If you plug the number 12 into Robin's formula, the theoretical speed limit ceiling for a number that small is only about 1.62.
Right.
But as we calculated earlier, 12 has an actual abundance of 2.33.
It shatters the ceiling entirely.
It completely ignores the limit. The number 60 breaks it as well. The number 2,520 breaks it.
But what Robin proved is that if the Riemann hypothesis is true, 5,040 is the absolute final integer in the history of mathematics to ever breach the limit.
Yes.
Like, if a computer or a mathematician finds even one single number past 5,040 that pokes its head above that line, the Riemann hypothesis is false. The million-dollar problem is dead.
It's totally dead. And that reality introduces a terrifying dynamic regarding safety margins.
What do you mean?
Well, you might naturally assume that as numbers get massively huge into the billions and trillions, they just run out of steam.
You know, like diminishing returns taking over. They should naturally settle down and stay safely below the boundary with plenty of room to spare.
Right. But Robin proved there is zero structural safety margin. The numbers most likely to break the rule, the worst-case scenarios, are what he categorized as superabundant and the colossally abundant numbers we just discussed.
Oh, because they're optimized.
Exactly. They do not settle down. They are mathematically engineered to absolutely maximize abundance relative to their size, meaning they are constantly pushing right up against the glass of that ceiling.
Oh, wow. They're structurally designed to touch the leading edge of the envelope. So they are the permanent danger zone.
They are. If a counterexample to the Riemann hypothesis exists, it will be found hiding among those colossally abundant numbers.
Okay, I have to push back on the premise here, though.
Okay, go for it.
Because we know exactly which numbers are in the danger zone, the colossally abundant ones.
Yeah.
And we know the exact blueprint to build them, hoard small distinct primes, and stack the exponents to erase the discount. So if I have the architectural blueprint for the building, and I know exactly where it's located, why hasn't a mathematician just used basic calculus or number theory to measure it and prove it stays under the line forever? Like, why is this still unsolved?
That is the big question, and the sources outline the tragedy of this proof perfectly. It all comes down to a devastating mismatch in precision.
A mismatch in precision.
Yeah, we have an insurmountable gap between the microscopic target we are trying to hit and the inherent slop in our mathematical tools.
Walk me through the target first.
Okay, so Robin's criterion doesn't just ask us to roughly stay below the ceiling. It hinges on measuring a tiny second-order correction term that dictates exactly how close these numbers get to the glass.
Okay.
And as numbers get bigger, this target correction term shrinks exponentially. It becomes phenomenally small.
So we are trying to measure a microscopic gap.
Yes. Now look at the tools we have to measure it. If you try to prove this using basic elementary math, specifically our standard tools for counting prime numbers, that elementary method carries a built-in margin of error, a slop. Slop, okay.
And the mathematical reality is that this margin of error only shrinks linearly.
Oh, I think I see the problem. It's like, imagine you're trying to measure a gap that is 1 millimeter wide, but the markings on your ruler are a full centimeter thick.
That is a perfect analogy.
The margin of error in your ruler is a full order of magnitude larger than the target you were trying to measure.
The slop completely swallows the target. As you move toward infinity, your margin of error becomes 10 times, then 100 times larger than the gap you were attempting to verify.
Wow.
And crucially, the sources emphasize that this loss of precision is not because we don't understand the exponent geometry we discussed earlier.
Right, we know how the exponents behave.
We know exactly how they behave. The limitation sits entirely in our inability to count the underlying primes with enough precision.
Oh, man. So to shrink our ruler's markings down to the size of the target gap, we would need impossibly precise information about how primes are distributed.
Yes. You would need information that is mathematically identical to possessing Riemann hypothesis strength knowledge. No way.
It is a brilliant, agonizing catch-22. We successfully translated the impenetrable complex plane into a simple problem about division, but the ruler we need to measure that division requires us to have already solved the complex plane.
That is maddening.
It really is.
But the text doesn't end there, right?
Yeah.
Because mathematicians have found ways to simplify the search and bypass some of that complexity. Like the sources spend a lot of time on something called the Aloglu-Erdős formula and an epsilon dial.
Oh yeah, this is one of the most elegant workarounds in modern number theory.
Yeah.
Because normally to find these dangerous, colossally abundant numbers, you would have to search an infinite dimensional grid of possibilities.
Right.
You have to constantly ask, how many 2s do I use? How many 3s? What about the 17s?
It's too much.
It creates an infinitely complex, multivariable search space that would crash any supercomputer.
But the formula collapses that.
Yes. Using the logic of diminishing marginal returns, mathematicians prove that this infinite search can actually be collapsed down to a single master parameter, a continuous dial denoted by the Greek letter epsilon.
I want to make sure we understand the mechanics of this dial.
Yeah.
Because from what I gather in the text, it operates like an automated cost-benefit analysis algorithm.
Okay, yeah.
Imagine you are building a massive number and you have a budget.
Right.
The algorithm constantly weighs two options. Is it mathematically cheaper to add a brand new prime, like 11, which costs some weight but gives a massive multiplication boost? Or is it cheaper to square a 2 you already have, which costs less weight but only gives a marginal fractional boost?
That is a phenomenal way to visualize it. The epsilon dial basically sets the exchange rate for that internal economy.
Oh, that's cool.
Yeah. By simply turning this one dial, you change the threshold of that cost-benefit analysis. The formula automatically balances the primes and the exponents perfectly, and it just spits out the exact colossally abundant numbers in order.
The sources actually provide the results of a Python script that sweeps this dial, which makes the theory wonderfully concrete.
Oh, yeah, you love that part.
So if you set the epsilon dial to 0.2, the formula calculates the optimal balance and spits out the number 12.
Right.
And as we know, 12 breaks the speed limit. Its ratio to the ceiling is 1.43.
And then as you turn the dial down, making the epsilon smaller, the numbers generated get exponentially larger. They start bringing in new distinct primes, expanding the recipe.
Right, so if you turn the dial down to 0.05, the formula generates the number 2,520.
Okay.
It still barely breaks the ceiling, sitting at a ratio of 1.01. But then you turn the dial down just a bit more, past that critical 5,040 cutoff.
Here we go.
You set epsilon to 0.02. The formula generates a massive, colossally abundant number around 370 million, and its abundance ratio drops to 0.968.
It drops safely under Robin's ceiling.
Exactly.
And from that point onward, as you sweep the dial towards zero and generate numbers with hundreds of thousands of digits, every single colossally abundant number tested sits strictly beneath the 1.78 speed limit.
It is incredible to see it in action. Like, we can literally turn a digital dial and watch these massive, structurally optimized numbers behave exactly as the Riemann hypothesis predicts they should.
Yeah, it's so satisfying.
They push right up against the glass, but they never break it. Yet, because of that prime counting slop, our blurry tape measure, we simply cannot prove mathematically that the glass will hold together all the way to infinity.
Right. We have the exact blueprint for the house. We can see the first trillion floors are built perfectly, but we just don't have the tools to guarantee the roof never caves in.
Man. Well, let's pull all of this together, because the journey we've been on today completely shifts how you view abstract math. We took the Riemann hypothesis, arguably the most terrifying complex problem in modern mathematics, and we stripped it down to a strict cosmic speed limit on how heavy a number's divisors can get.
Yeah, and we learned that this abundance is driven almost entirely by the act of hoarding distinct primes, with the exponents just acting as a tiny fractional adjustment trapped between 0.61 and 1.
And most importantly, if every number past 5040 obeys that 1.78 times log of n speed limit, the Riemann hypothesis is true.
Simple as that.
And hey, since you like the mathematical graph of the distortion factor, I can build another clean chart plotting the abundance of the highly optimized, colossally abundant numbers against this 1.78 times log n speed limit to show you exactly how close they get to breaching it. Want to check that out?
Oh, that would provide a striking visual representation of the permanent danger zone we've been exploring. I'd love to see that.
It really puts the scale of the math into perspective.
Yeah.
So as we wrap up this deep dive into the arithmetic boundary of the universe, what is the ultimate takeaway? Like, what should we be left mulling over?
I'd say consider the structural irony. We have built almost all of our modern cryptography, our digital security, our banking systems, all of it on the apparent randomness and chaos of prime numbers.
Right, the unpredictability.
We rely heavily on the assumption that they are unpredictable. Yet, when we look at the math today, we see that when you bundle those exact same chaotic primes together with the goal of maximizing their divisors, they suddenly snap into a perfectly predictable, incredibly rigid geometric structure.
Wow.
A structure that dictates the absolute boundaries of arithmetic itself. It forces you to wonder, are prime numbers actually chaotic, or are we just too zoomed in to see the architecture?
Wow. From impenetrable complex analysis to a beautiful, rigid architecture of basic division, the X-ray machine of mathematics might just work after all.
Indeed it might.